Our next speaker is so cool that his Twitter handle is just his first name. In fact, you won't meet anyone ever that also has his first name. He'll make sure of that. When he's not in his mountain lodge carving axes from metal left by meteoroids, he's teaching fairies how to love, and we brought him here to tell us about monitoring and metrics. He is Caskey Dickson.
My name's Caskey Dickson, yeah. I do all those things. That's all absolutely true. But we're going to talk about metrics and the nature of numbers and what they mean. I spend a lot of time thinking about numbers, too much time, in fact. If anyone in the audience is a statistician, you just forgive some of the lies I'm going to tell, because I'm going to talk about numbers from an operations perspective. Some of these slides do have some small text. When I saw how big the room was, I went through quickly and blew up some of the text. So if you're in back, I apologize. There is the URL there. You can follow along, or I'll tweet it out later. So what are metrics? What are they? All right. This is an important question because we deal with them. Who here has numbers that they have to look at on a dashboard or they collect? Really? You don't have any numbers in your organization at all that you track about your services? People, please. Okay, that's good. You're here, you came, we'll work forward, you'll learn, and you'll do more. Okay. The problem with metrics is that, it seems like it's a simple idea. I collect some numbers, I look at some numbers, I measure some, and I compare to what they looked like last week, and I've got metrics. But the question of what a number really is and how you use it varies based upon the mathematical properties of what you're measuring and how it can be compared, because you can't compare some kinds of numbers to other kinds of numbers. You can, for instance, measure that the temperature in the room is 71 degrees right now, and a minute ago it was 73 degrees. An illogical operation would be to take those two numbers, add them together, and say, over the past minute and a half, it's been 143 degrees. It doesn't make any sense. You don't add those numbers together. You can average them. There's certain other mathematical things you can do. Similarly, if you know that you had 150,000 requests processed by a particular serving unit a minute ago and 151,000 processed as of now, 1,000 things happened by subtracting them. But you also wouldn't add them together. So there are other kinds of things you can do. Back in 1936, a bunch of scientists around the world tried to get together to come up with what does it mean to measure things scientifically, with actually put data together. This was a really big question, and we were talking like complex measurements. We're saying, if I want to count how many sheep there are in a pen, what does it mean to say there are 4 sheep in this pen and 6 in that one? What things make sense in science to do so that we're doing legitimate math when we're gathering data about experiments and so on? So a group got together for 4 years, an international consortium around the world. They met, they debated, they negotiated, they tried to figure out how do you define what a metric is and what's valid about it. This is where they got to after 4 years, the assignment of numerals to things so as to represent facts and conventions about them. So the assignment of numbers to things. That's 4 years of work. And that was the preliminary report in which they said, you know what? We need another 4 years to keep working on this problem because that's not good enough. Don't know what happened 4 years later. I think they ended up just quitting, saying this is too hard, trying to actually come up with what do numbers mean. All right? So this is a very big problem. But we all gather metrics. So when we say we're gathering metrics, what are we actually doing? Well, a metric is simply a named value at some specific time, right? It's a number, has a name, and there's a timestamp on it. But names are complex, all right? What are the 2 hardest problems in computer science? What? Naming things, caching validation, and off by 1 error. So those are the 2 hardest problems in computer science, right?
And counting.
And counting, yeah. So the metric identity is actually something which is a complex multiple in an identity space, where at every single intersection of all combinations of those identity values, you have a particular sequence of timestamp values that represent a time series that covers data that you're measuring about something. The actual values themselves, though, can come in multiple different kinds. There's counters, there's gauges, there's percentiles. These numbers also are things that are called nominal, ordinal, interval, ratio. And then, of course, you've got derived metrics, which are things like they're done by taking 2 existing measurements and combining them. Okay, all of these things come into play when you're trying to start gathering numbers. And if you do a bad job of picking what names and where you're going to assign and save those values, you aren't going to be able to ask good questions about what's going on inside your system. So, and of course, timestamp. So here's an example, which you won't be able to see at the back of the room, which basically represents a counter at a particular time, sometime August, sometime in the future, from a particular web server serving a particular website, right? So when picking how to collect these values, we actually have 3 different controlled variables that decide how much data we're going to be consuming. We have the resolution of the data. How often do we gather that metric or have it pushed into our system? Is this a metric that I want to measure every 6 seconds, every 6 milliseconds, every 6 days, every 6 months? There's the latency. After you do collect that data, how quickly can you act upon it? Some people's monitoring systems take hours before you can actually get actionable data. Sometimes that's okay. Some take seconds, some take minutes. And finally, diversity. How many different unique time series are you actually trying to collect? Now, these 3 properties actually, whether they're high or low, high resolution, low latency, high diversity, low diversity, they actually characterize the types of operational use we make of data. I use 4 things to describe the types of actual collection that people are doing. Operational health and response, they have to be high resolution, all right? Now you need them to be gathered every minute, every 10 seconds. Some people use monitoring systems that gather every single second in order to get the real-time view of what it is that's going on in your system. They have to be low latency. Knowing what your server was doing yesterday isn't very useful if you want to be able to respond to it being down. If it takes a minute and a half for you to process your data pipeline that tells you whether your server's up, the fastest you can respond to an outage is a minute and a half plus 1 second, or however long it takes you to answer the page, right? And finally, high diversity. You need to know about a lot of different things about a lot of different parts of your product. So the operational health response is the hardest problem there is. But then when we get all the way down at the bottom, I'm going to skip over the middle ones, we get to things like product management. How many 7-day actives do we have? How many 30-day actives? These are very low resolution, very high latency, and very low diversity numbers, like how many customers do I have? So there's a continuum of how we collect this data, and the way in which we collect it impacts what we can do with the data. Oh yeah, there's an arrow. Just for completeness sake, because I realized I was doing this little binary count on each of these things, I ended up with these other 4 categories. I'm like, what are these other ones? When do you need low resolution, low latency, low diversity data? And the only one that I've been able to come up with is load balancers. They have a very specific amount of data. Like, is that back end up? Can I send traffic to it? Right? But those other 3 categories, haven't been able to figure out anything with that uses those. If you can think of some ideas, let me know. So, operational health and response. This is where the most important metrics are because these are the ones that keep our business online. Which metrics are they? Well, whatever is the right metric that tells you what your service is doing, but that varies based on what kind of service you are. Someone who's a cloud hosting provider, they don't care about micro optimizations within the app that's running on it because that app belongs to their customer. They care about things like CPU utilization, packing, overcommit of memory, and so on. But also, the operational health and response problem is the hardest one to do because you need the most amount of data because ideally, the moment something goes wrong in your service, there is one graph, one number that has suddenly gone up, gone down, flatlined, changed level. If you already have that metric being collected and you can see it, then you already know exactly where the problem is. Oh, look, data center 7, row 14, blade 9 in rack 4 is on fire. Because that's the only one that changed. But you have to have been collecting the data at that low enough resolution or even know that. Or maybe you want to collect data on disk queue length, disk command queue lengths on a per spindle basis throughout your entire fleet, right? Well, you rapidly end up with a lot of data to ingest, and this begins to impact things like latency. But if you can know immediately that the reason your application service is slow is because 4 layers away in the storage layer, there's a spindle that's having read errors, then you can connect those things together. And you don't go and find things by SSHing into machine and say, is this working? Is that working? Okay, it's not that. Instead, your data automatically points you to exactly where the problem is, and you go fix the problem right then. You don't wait to play, well, is it in this server? You don't start SSHing from machine to machine to machine. You have a metric that says, this is failing right now. All right, oh yeah, so what can go wrong? And do you have enough metrics to differentiate between each of these different kinds of errors in a way that lets you respond to it, right? Bad code. Always bad code out there. There's always bugs. Bugs are always a problem. Bad hardware. Can you tell if a CPU socket is failing inside of your fleet, therefore causing higher error rates in your application because of a hardware problem in the device. Or if one of your switch ports, network switch ports, is failing and it's randomly flipping bits on some packets only between two particular source and destinations. If the first two bytes of the IP address are the exact same thing, then it randomly flips bits in the middle of the packet. Only under that circumstance, right? As we get bigger and bigger and bigger fleets and more complex environments, these things will happen. If you're running, who here has more than 1,000 machines under management, right? So every single day, you're executing at least 3 compute years. Every day. It's just math. 1,000 divided by 365 is about 3. Every single day, imagine you have one server, you're on one piece of software for the next 3 years. Will it have 0 faults? Probably not, right? How many people have 10,000 machines under management? Anyone? Few? Yeah. Congratulations, you're doing 30 years a day. 100,000 machines. All right? Couple? No? Well, point is, you see how it works out. That much execution and that much failure, always going to get really weird stuff going on. So bad data, bad configuration, resource exhaustion, combination of all of the above, or none of the above. Ideally, you have metrics that are actually able to help you diagnose which of those kinds of things is going wrong because you have some labeled value that hints at that. All right. So where does data come from? This is an example of raw data involving memory information and a network card in 2 different views. Proc.mem.info gives you these counters. SNMP walk gives you this information about it. You don't need to worry about the specific values here if you're in the back. The point is, when you look at proc.mem.info, you get values that contain things like total amount of free memory, the buffers assigned, and whatnot. If you do an SNMP walk, you get similar information about CPU utilization. You can get network interface speed and so on. But these values, do not just blindly scrape them and log them because they're designed to solve different problems. You want operational intelligence about your service. So you don't want to just take the raw buffers there, 54.8.704, right? Because that's designed to be useful to the kernel for what the kernel needs to be doing of memory accounting, not you as an operations engineer. You need to massage and manipulate that. So getting into, wow, I bumped the font sizes. Now everything's like a little out of alignment. So there are 4 basic kinds of numbers. There's nominal numbers. I'm going to go into a bit more detail in each. Nominal, ordinal, interval, and ratio. And the kind of math you can do over each of these different numbers varies based upon what kinds of things you do with it. So nominal numbers, these are the most basic kind of metric. That's where you've taken a number like 42 and you've assigned it a meaning, the meaning of life, right? That's it. Now, the problem with nominal numbers is people sometimes mix them up and they start doing wrong things with them. With a nominal number, all you can do is have identities related to them. You can say that, well, this is 13, and I know that I defined 42 as the meaning of life, therefore, this value is not the meaning of life, and that's it. And this shows up a lot in things like SNMP, where numbers map to a table of specific values, but you can't say that just because this is a CSMA CD Ethernet connection, which is type 6, if I have a type 5 connection, that's 1 more. No, because it's fiber, right? It's just 2 completely different categorical things. But you can do things like take the mode and do frequency distribution. It'd be perfectly valid to say, you know what, show me a distribution of all of the network port types in my system, right? But you would never add together those port type numbers. Next is ordinal. Now, the nice thing about ordinal is it builds on the first kind because you can do all those same kinds of equivalence relations, but you also get an ordering out of it. If I came in 42nd in the New York Marathon, unlikely, and someone else came in 20th, you know that 42 is greater than 43 is greater than 20. However, that doesn't tell you anything about how much faster or slower I was than that other person, but it does give you a total ordering, and so it has some value. Similarly, host names. Host names, if you have a naming system that identifies where a particular machine is, then you can know that if this machine is named AGBF and the other machine is named AGBE, then this one is to the right of the other one in the data center. Or if it has a bigger number or a smaller number, then you know it's either higher or lower in the rack, right? Version numbers. We can always tell version numbers apart, sort of, right? But we have a lot of complex rules around parsing them. And now I can know that version 3 of a piece of software is newer than version 2 of a piece of software, usually unless they reset the numbering, but let's not get into that. That doesn't tell me about how many releases happened in between those 2 versions. You know, anyone ever been in a situation where they've got a system that has a version and they got the version they got to go to? It's like, well, can I just go straight to this version, or I do need to do all these incremental upgrades along the way, right? And how many are there? Without extra information, those two things don't tell you anything. So that's ordinal numbers. But you can still do some statistics over it. You can take the median, you can percentile. There's also a couple of other advanced ones, Spearman correlation. Who knows what Spearman correlations are? Good, no statisticians. Good. So no one's going to call me out on all the lies I'm telling. Interval numbers. So this, you've got ordinal and relational, and you're now at the point where the intervals between them have meaning. We know that 73 degrees is 1 degree hotter than 72 degrees, and that's the same difference in hotness as 72 and 71. Similarly, I could take a 42 terabyte storage array, subtract out the 40 terabytes that are in use, and I will get 12 terabytes. I'm sorry, 42 to 40, I get 2 terabytes. Similarly, if I've got another array which has 98 terabytes, and it has 96 terabytes in use, same 2 terabytes. I can subtract those two values from each other and then compare the resulting math that came out of it to each other, and I have a meaningful value. If I have less than 2 terabytes of storage, then I know that what I need to put on there will fit on either of those two storage clusters, right? However, if we do a ratio on it, one of them has around 4.5% or 4.7% disk free space. The other one has 2% disk space. But they both have the exact same amount of free space. See what I'm getting at here? Where you can't directly compare the percentages and get a meaningful value, because without knowing what it was derived from, you don't know, do I have enough space to store an additional 2 terabytes of data? Here, you've got the mean, you have the standard deviation, and as well as a couple of other more exciting kinds of math. All right, ratio numbers. So this has interval, ordinal, and relational attributes, and you can then start doing interesting comparisons like what we were doing before, where 75% is less than 85%, and you usually start with an interval number, you do a bit of math, and you get a ratio. Is your system failing if it's got 90% used disk space? Maybe, maybe not. You need more information to do that. But you need to be thinking about, as you're creating those, how many here have a default Nagios rule or an alert rule that says, oh, look, warn me if I'm over 95% disk utilization? Yeah, we all do. But what does that mean, right? 95% disk free on my laptop, and my laptop's hosed. 95% utilization on my laptop's not going to be very useful. 95% utilization on my storage cluster, probably fine. That represents petabytes of additional storage space all ready to go, and that's just my steady state, right? So context is everything. With ratio numbers, you can do geometric mean and logarithmic reductions on them. So those are the types of numbers that are out there. Now, gauges and counters, we all care about these. Everyone's got gauges which measure a specific value. Some gauges have meaningful 0 points. Not all of them do, right? Temperature is a great example of a value that has a meaningless 0 point. 0 degrees doesn't really mean anything. However, kernel mode CPU seconds consumed in the last minute, if it's 0, then that's a meaningful number, right? You can't go below 0, and you can add zeros and zeros and zeros and another one, and you still get some meaningful data out of that. But adding a bunch of 0 degree temperature readings together doesn't give me any meaningful information, right? Because it's just an infinite scale going either direction. All right, so the reason to keep track of this is because I can sum CPU utilization across servers, but I can't, it wouldn't make any sense to sum drive temperatures, right? It was not very meaningful, not a very useful computation. So naively, gauges and counters have similar uses, but the 0 point value may or may not be meaningful, and it depends on exactly what you're measuring. All right, so let's work a couple of specific examples. If you were a data center provider, these are 3 metrics that you probably would want to actually take a look at. Okay, memory, network, CPU. Sorry for the formatting, but this shows the raw source of data from either SNMP or from proc, showing the entire memory footprint of that machine. Now, I don't want these raw values. Instead, I need to construct a multidimensional namespace in which I can copy those raw values into, so I then have something I can act upon from an operational perspective. So naively, we just start with memory. That's our first part of our name, but there's this big space in the middle that we're going to fill in with details about that particular measurement. So what do we need to add to this? Well, host name would be a good thing to add, right? This is the amount of memory on that host, 66 gigs. Yeah. That's not necessarily useful because those 66 gigs are being partitioned in a lot of different ways. I want to know not just that there is 66 gigs of RAM in the machine. I want to know what each of those 66 gigs are doing. So we're going to add another label called free. So all of a sudden I've gone from 66 now to 46 gigabytes of free memory. But there are even more types available. Now this is an example of a closed set of overlapping spaces because the status free would be duplicated in many different locations as the same meaning, but hostname wouldn't be duplicated. Hostnames are unique, hopefully within your environment, otherwise you've got much bigger problems. And so by combining the hostname and the state of that RAM, I now know something about a specific block of memory inside my data center. Next, just because it's free, the kernel actually has two separate counters. A counter for free swap space and a counter for free physical RAM. So I need to be able to differentiate between those two. But it reports out one value as total free memory. So you got to tease out these values and get different time series. And what you end up with is this. Now this is the typing where it's a fully qualified type of my memory metric would be memory qualified by hostname, status, and whether or not it's physical swap. It's an interval-based value, it's a gauge, and it's zero-based, which means it has a meaningful 0 point. And these are all of the metrics that I would get out of just tracking the memory status of my host. Instead of just 90% used, I need actually, it's about 8 different metrics to track the full state of my memory on a per host basis. Now, if all of a sudden I have a memory issue or I'm experiencing memory pressure, by looking at these metrics, I can pull out the one that says, oh, this host right here is the one that's experiencing a sudden loss of free headroom, and I know that I've set rules that I want at least 4% headroom available on all of my servers. Or maybe the block cache is being pressed. I want to make sure that at least 20% of my RAM is being used for block cache at all times on a per server basis. And you can then find out when an individual server is failing. And your metrics tell you exactly which host it is that's having that problem. You can go on it and see, okay, what's running on this machine that's causing the problem? As opposed to just saying, well, across my fleet, I'm using 95% of my RAM. Okay? So by pulling out individual values and tracking them separately, you can get targeted diagnostic information about specific problems. Now we can start adding derived metrics. If we take those metrics and we sum them across all states, then we know the total amount of physical memory in our system. If we sum them along all non-free states, then we have the non-free memory. We can then combine both of those into our percentage memory load on a system-wide basis and on a per-host basis. These standing queries would allow us to directly access the meaningful information and then write rules that are tailored to the individual environment. And when the rule fires, I'll know which specific host was having that specific problem. Okay? Now, all this is possible because of those attributes of this being interval, gauge, and zero-based. That defines the math, what is valid math over these metrics. All right, same thing can be applied to CPU utilization, except it's hostname, which core it is, and what mode the counter is counting. So this would be a series of metrics, just like before, for every single possible CPU execution mode, and there'd be a counter incrementing for every tick that was being consumed on a per CPU basis within the kernel. And then I can sum across all that, and if you start discovering that you have specific cores that are not executing the same as all the others, they're not evenly loaded. There was a great paper that came out earlier this year that pointed out that there is a serious flaw in the Linux scheduler where under certain workloads, individual sockets would not get rebalanced. You'd have processes being starved of CPU even though there are cores that are completely idle. And that's because of the way the Linux kernel does the rebalancing of processes among individual cores during the scheduler. It's a great paper. And it turns out that, yeah, you could be wasting, depending upon workloads, up to 12% of your total CPU capacity. 12 or 20. The point is, it's a big number. All right, network I/O. If you're tracking individual interfaces, then you'll be able to find what type of things are happening. You'd be doing what type of packet. Is it a unicast, a multicast packet, a drop packet, an error packet, a broadcast packet? And if you're counting all these things, then you know, based upon the nature of the metric, what type of computations you can perform over the metric. And you then also have targeted data like, oh, look at that. I've got a line card that's failing because every piece of traffic that comes in and out of that host of this type is an error. All right. The hardest part of all of this, though, is storing all of these metrics. Now, the good news is we've got better tools in the last couple of years. Specifically, OpenTSDB came out many years ago, and it's now a very robust platform. Prometheus. Who here's tried Prometheus? couple, you got to try Prometheus. It's awesome. All right, but it is the first major system that's come out that natively understands the concept of multidimensional metrics that are then summed at runtime to be able to give you both aggregate and detailed alerting on individual errors. Great system. And HBase. All right. Of course, you might not be a host-specific provider. And this isn't a transform you would do over individual values. It's like if I care about something different, then you change the set of labels that you're assigning to those values as you collect them. Remember, all this is coming from the exact same kernel counters. But by changing the sets of labels I'm attaching to them, it changes the actions I can take on those metrics when I go and try and analyze them, or when an incident happens, what type of data is available to me, without having to go and start SSHing into machines, right? The last thing you should be doing, hopefully, before you go and try and solve a problem is, I'm going to start SSHing in server after server after server and find the one that's not doing the right thing. Instead, your dashboard should already be presenting you a metric that's classified in a way that's operationally meaningful to your service, so that you can go directly to where the problem is. All right. So, metrics are gathered for a specific purpose. The design of your metric namespace needs to be relevant to how you're actually going to use that data. Don't just take your monitoring system out of the box and have it collect all those metrics and present them. Think about what you would want to do with that piece of data and label it accordingly so that when it does change value, it gives you actionable information from an operational perspective. And the existing metric names are all terrible because they're designed to solve different problems. SNMP metrics are named and organized in order to make managing network switches easier. The proc namespace, those are just internal kernel variables that was whatever most convenient for implementing the kernel memory management and the CPU counters. Make sure that when you do decide to collect a metric, you know how you are going to use it from an operational perspective. Otherwise, you're just gathering data for the sake of gathering data. I mean, I like a nice big dashboard with a bunch of numbers that move, but I have many dashboards that I've created where I look at it and like none of these numbers ever move in a way that lets me do anything. So why did I even bother creating that? Make sure that your dashboards show you things that are going to indicate specific failures that are relevant to your product. And you may find out that instead of a giant wall of charts, there might be 1, 2, 3 that actually drive to the heart of what your product is and what's important. And when it moves, then you know you need to act. You may be gathering the exact same counters under different label sets for different purposes, right? There's nothing wrong with that. Don't think that, oh, I'm already collecting CPU utilization, and so I don't need to collect it on a per process or per socket basis, because if it's relevant to you and your product, then you want to do that. As a virtual hosting provider, knowing the per socket behavior of individual cores is important because I need to be able to find failing hardware. Fix your data store. This is the biggest problem, is that there are very few systems out there that allow the collection of these types of complex multidimensional metrics. Yeah, keep in mind what you're going to do with your data when you collect it. Sound good?
Thank you so much.
Do you do any postmortem on the type of metrics that are useful and then discard some of the metrics? And so,
absolutely.
How do you go about doing that?
Well, in regards to doing postmortems on the metrics, essentially one of the things that we heavily track is basically time to detect SLA failures. We've established an SLA around time to detect and around time to diagnose. And if it turns out that we violated that SLA because it took us either too long to detect it because we weren't looking at the right particular counter, this value went like that, but I was looking at an aggregate and it didn't change until 20 minutes later so I could detect it. So that's part of the postmortem process, is getting into why did it take so long to A, trigger an alert that something was wrong, and B, what data wasn't available in the right form and in the right expression that made it take longer to diagnose. So if I might have a very quick time to detect, but I didn't have a time series that gave me the specific detailed information. So that's part of the postmortem. Those are repair items that come out of it, is to create new metrics, or usually the throwing away metrics. That only happens when we discover either a noisy rule that doesn't apply anymore, or we begin to look at how much data we're collecting. Someone says, you know, we're really spending a lot of money on storage for metrics. But I have another presentation I give where I do the math on a reasonable size service. You can easily collect 400 gigabytes a day of metrics, and that's just raw time series. And that begins to add up. Terabyte here, terabyte there. Eventually talk about some real amounts of data.
Have you tried using statistical significance tests on series of metrics, and if so, what worked and what didn't?
So have I tried using statistical significance? Okay. There is one thing I've been doing that relates to that, and it's about sensitivity and selectivity of metrics across the data set, where I identify time periods when I really would have wanted to know what was going on, and I try and figure out which metrics were doing interesting things at that time. But that's not productionized. That's me doing data experiments over the time series that I have. So I don't have anything operational that does that, but I do perform experiments like that to try and find values of interest.
Is there a name for the category of metrics or information that's really second derivative? Meaning that I really honestly don't care usually if a disk is 95% full or 25% full. What I care about is it going to fill before I can do something about it? And it's kind of that, if I get the alert it's 95% full, and then a second later I get the alert it's 100% full, 95% didn't really tell me anything.
Yeah, I kind of lump all that under derived metrics. And yeah, static capacity-based rules are really, really bad. What you really want are predictive rules that say, I'm going to compute based on all of my first-order direct metrics. What is my predicted amount of, what is my predicted data horizon for storage, for instance? And I want to alert if I ever have less than 90 days of available storage. So yeah, I don't have a name for it. I just call those derived metrics. And under capacity planning, just about everything should be a forecast type metric in order to tell you, I better order some new servers because I'm about to be full.
You didn't talk much about the multidimensional one. So what are some of the guidelines when you're picking a multidimensional? Orthogonal? Is it orthogonal? I mean, what else do you consider when you're...
When I say multidimensional, remember, we're talking about these dimensions here. This is a three-dimensional metric. The dimensions are host name, the status of the memory, and whether or not this represents a swap RAM or physical RAM. I'm not talking about two numerical dimensions. It's the dimensionality of the space in which this variable lives. So this is a three-dimensional space, each of which contains a single-dimensional time series, because time series are all single-dimensional. So you would iterate over each of the values in that space. Now this is where you get the combinatorial explosion, because, for instance, if I'm going to track memory on a per type basis, I get 8 metrics per server. And if I've got a million servers, then I now have 8 million time series that I'm collecting every minute. And so you end up with data explosion. So you got to be careful about adding in dimensions that you don't really need, because every additional dimension multiplies the total number of time series that you have to store. And the good news is systems like OpenTSDB do very, very well with horizontal scaling of metrics. Many do not. If you're still using who has RRD-based storage? No one? Oh, great. So good. Well, RRD is an example of a system where each time series is stored 1 per file. And so it's very hard to have an 8 million metric data store, or in my case, hundreds of millions of metrics in a data store if there's 1 per file. And that's the main mechanism for managing it.
All right, can I get another round of applause for Caskey? Bill is big and grumpy, and you will know him. He'll make sure of that.